Hello, my name is Andrew Foster. I'm born and raised in Tampa, Florida. I'm currently a rising senior at the University of Rochester studying chemistry and math. Additionally, I study at a separate institution called the Eastman School of Music, where I'm getting a bachelor's degree in horn performance. Before I start talking all the weeds and details about science, I would like to just do a communal 5-second deep breath. I've got multiple high heart rate notifications, so I just want to practice the centering technique. If anyone else wants to join me, you're invited. Just trying to take a deep breath through my nose and out through my mouth. Thank you for your patience. Before I begin all the scientific details, I'll be talking about this both in a highly scientific manner and then also in language that is accessible to the public and non-scientists, because I think being able to explain our work to all types of communities is very important, especially when funding from politicians and the public is not always guaranteed nowadays. So first up, I would like to show you a video you probably saw yesterday from Dominic's presentation. The video is the self-healing crystal ditorpedoyl biphenyl. This is really crazy just to think about. Scientists over 100 years ago, if they saw this, they would be on the floor like, what is happening? But we're so used to seeing spending self-healing crystals now. And then I'm thinking just about the research we're doing now. I'm very excited. Hopefully we look at molecules on such a fingerprint level that hopefully in the next 100 years, this will just be Raman and terahertz will be like modes of like chemistry analysis techniques.
Yes.
Sorry, next slide. Okay, so originally ditorpedoyl biphenyl was researched and studied a little bit in this paper that was published over 2 decades ago. They proposed 3 foreign polymorphs, both which form 2 and form 3 had an irreversible transition upon heated and went to form 1. They did not discuss or mention from their DSC any possible low temperature polymorphs. However, the DSC are the top 3 figures. They're a differential scanning calorimetry technique. Essentially, all the peaks represent if there is an endo or exothermic heat exchange, if there's a reorientation of molecules or change in polymorphs. Additionally, the paper only discussed the torsion angle or the dihedral angle of the biphenyl, which I'll discuss later about the collective variables, but which is just unique because we're also been studying the torpedoes and their movement. And we're studying molecular dynamics, so yes, the crystals and molecules are moving. The motivations to understand what is happening, the big right spectrum is around the spectrum of variable temperatures. You see at the lower temperatures, or with the DFT simulations, you get much more clear ordering peaks, and then above around 180, 190, you see much more, 190 Kelvin, you see much more smoothing, broadening, smearing happening, so there's much more believed to be disordered happening throughout the crystal structure. The bottom left figure is just an overlay. You see on the right the DSC, this is just a zoomed in part from the 140 to 220 Kelvin. But the left figure represents that even though the polymorphs are changing throughout temperatures, the overall large bulk structure is staying relatively coherent throughout. And then just to go further into detail, this is an example from the crystallographic zip file for the 170 Kelvin polymorph. And you see on the same, just one ditorpedoyl biphenyl molecule, there's the green represents there's only 3 possible sites where the torpedo can be, whereas the red ones represent there are 6 possible symmetry sites or positions where the torpedo and collective variable can go. And just to explain what a collective variable is, since we're studying such a large molecular system, is able to help put all the details into a much more clear and confined way and possible mechanism to propose what is happening. You can have good collective variables or bad collective variables. A simple one is just a bond length or bond distance to measure if bond is breaking or happening. You can do just 3 atom angle, or you can do a dihedral angle, which is primarily what we've been focusing on, because throughout some of the other talks you've seen a lot of systems have a statiator or a part that does not rotate, or a molecule group that does rotate, and specifically we have the phi and gam, which are the 2 torpedo groups experiencing rotation, and then psi is the rotation from the biphenyl. And then this is just a quick video from my research over the past 2 years on the system, just to represent a conformational change that happens. This video is 30 seconds long, but it's 800 picoseconds. I won't play the whole video for time's sake, but it goes back. And then quick, if you're unfamiliar with computational chemistry, I'm doing classical MD, which is that taking into account for all the nuclei or ab initio techniques, because we're more focused on just where the covalent bonds of these torpedoes or biphenyls based on their location. And essentially, this is we're taking a scan or picture of a simulation every 2 femtoseconds or 10 to the negative 15 seconds, and then long-term running simulations for 200 nanoseconds, which is about 10 to the negative 9 time scale, and making a long snapshot picture video. And then throughout all these snapshots, this is a simple way of understanding how my data is worked up. The first figure, the x-axis, is just the time and picoseconds. So this is 190 Kelvin of one torpedo group. There is essentially just 3 sites where at this lower temperature the torpedo is really able to go, and then the bottom here is a histogram approach. So every, say, 2 degrees from the first figure, we just take how much of population site or probability will be at that state, and then you can kind of see there's a central peak, but you can start to see a little skewing along less likely to be, or more likely to be around negative 20, and then it's a shifter. Left side of this figure is a much more sharp, dramatic drop. And then from these figures, to calculate the free energy surface, you have to account for the KBT, or the free thermal energy, happening at the given temperature you're running the simulation or in real life. So you take the KBT and then also take the log of the probability of these population sites, then negative log, and then you get the free energy surface. And then this is just a similar approach for higher temperature simulation at 240 Kelvin. You once it goes through the final phase transitions, you can start to see more population sites for the torpedoes. You start to see 6 possible minimums. There's 3 sites per torpedo, so you can see when it's at a time in one of the sites, it's also in all the others of the 120 confirmation. And then similarly, you get free energy surface. This is stuff I did more at the beginning of last summer. I was originally studying the biphenyl dihedral angle, which now, after Dominic's talk, I want to add my future steps. I'm going to also explore this a little more. But this is just another one of the picture frame graphs, and then eventually the free energy surface. This is at 350 Kelvin. You saw the video. That was at 350 Kelvin. At that temperature, you're much more able to see that conformational change. But at lower temperatures, this conformational change is not really seen around negative 140 Kelvin. Whereas this left figure at high temperature, 350 Kelvin, is literally just always moving because there's so much free thermal energy. And then at KBT at around 350 Kelvin, it's just around 3 kilojoules per mole, so it's just really rotating. And then going on a little part of the summer, this isn't the primary focus of my talk, but we were comparing the population sites from the crystallographic SID files that were taken from Will Stoll back in Rochester with Bill. And we were just comparing the population sites, and there was, just through counting them, the frames and where the positions of the collective variables are, there is a relatively close overlap most of the time. And then this is the most recent updates on the project. You can see at lower temperatures, there's only 3 sites. The blue one's a dark purple or blue, and then over time, you eventually converges down to less higher activation energy to go over. You see much more free flow at around 350 Kelvin. 190 Kelvin was good on this first one, but it's currently being rerun and not on all temperatures currently, just because there was some mess up in my convergence of that simulation, so I hope to have that fixed next week. And additionally, not all these graphs are skewed the same direction, which I think goes back to what we're seeing a lot of. Each torpedo is not symmetrical in the unit cell. I didn't mention the differences of the different polymorphs. I thought that was that yesterday, but just a friendly reminder, the 140 Kelvin polymorph has 5 molecules in the asymmetric unit. The 171 has 6 molecules in the asymmetric unit, and then 210 is 2 molecules in the asymmetric unit, and then above 220 Kelvin is the asymmetric unit, which is a little strange just because if you look, I hope next week as well to make new figures with more isolating what is happening, more so with the like green and teal ones, because you could possibly figure out a rate constant or time how these torpedoes are rotating, because it almost looks like it's a little jagged, almost like the rotation is happening, is getting stuck sometimes in one spot and being a little, almost like a flat tire rolling. So, some of my future steps, I hope to have them finished off the simulation later next week. I hope to also combine some of the thoughts Dominic provided yesterday. I'm analyzing the biphenyl torsion or diketral angle, and then also make a 2D for energy surface combining either the 2 torpedoes or also considering the phenyl orientation. These are 2 figures you're looking at on the right. They're both in radians instead of degrees. This is from a metadynamics simulation I ran last summer. The 25, or the very dark red, is very high kilojoules per mole, unlikely to be activated, unlikely to be populated there, as in the dark purple is you're much likely to see population sites of that orientation at that temperature. So you see just between 20 Kelvin, in the torpedo sites, you can see more possibilities of confirmations that way. I did other research this summer, and I attempted metadynamic simulations, but they weren't fully successful. I over-biased it, and then your simulations can converge the wrong way, so I hope, if needed, to retry that. And then I want to just also thank Ale, my grad student in the lab, for all the help he's provided me. Also Giovanni, who's been an amazing PI, taught me a lot. And then last summer, Maria McKelly, they taught me everything I know about computational chemistry. And then a huge thank you to Mike for letting me come back for a second year. I struggled a lot with my mental health over the past years, and I just want to say huge thank you. A lot of people don't know, but back in Rochester, I took his class in the spring. Back in December, I was really struggling mentally, and I even just dropped his class, and he went out of his way to check in on me and what was going on. And when I got back to Rochester before classes started, we got coffee, and I just want to say thank you for being a friend and caring about me. Being a young adult, it's not always easy. So. If there's any further questions, I'm also open to having a discussion because there's so much possibilities where this research could go. So thank you for your attention.
Thank you, Andrew, for your very short presentation. Thank you, Alfie, also for opening yourself to clients and questions. Yeah.
Can you go back to the slide about this slide? You said, could you say one more time about why the peaks are not symmetric?
The what are not symmetric?
The peaks? Like the 150, the low temperature on the right.
Yeah, so why is the one on the left kind of like one peak and the one on the right 2 peaks at 150 Kelvin?
150 Kelvin.
The blue. Right?
Yes.
So on the left, it's just like one barrier, right? And on gamma 4, you've got like 2 barriers. Right? It's peak shape. There's 2 peaks at 0.
If you look
At
at the
0,
blue
okay.
line, the blue line.
For gamma 4 on the right.
Yes, the 0, 1.
And there's the blue or the purple, right? There's 2 peaks.
Yes.
And on the gamma 3, it's just 1 peak at -50 or whatever.
Is this peak?
Yeah. Yeah, that, and the one next to it, right?
This like shoulder peak?
Yeah.
Currently, not entirely sure yet. Still trying to figure that out. It is the one way we've been trying to get more statistical data is by rather than running longer simulations, we've been trying to combine symmetrical units throughout the unit cell. And sometimes I originally had to rechange that approach, but then this has been the new approach, but it's not always, I'm wondering if the system's not always, sometimes, I mean, it's converging, but then it also can, when my metadynamics simulations I learned, it can converge the wrong way, be like, add too much energy to it, so that's a good question though.
Are gamma 3 and gamma 4 in the same chemical environment?
Next to each other.
Right, but in the crystal at 150 Kelvin, are they like in identical,
Oh,
like, you know, chemical environments, or is it a little bit different because of the symmetry of the crystal?
they're not like next to each other, but they're in different parts of the asymmetric unit.
Right. So, what do you? So right. So maybe that's why there's differences there, because they're in different chemical environments. And this is kind of the point, which we're thinking that each terp-butyl group kind of locks into place at a different temperature, because each individual terp-butyl group is in a slightly different chemical environment with a slightly different barrier and a slightly different potential energy structure, and that's why the phase transitions happen, where each terp-butyl group at a different temperature locks into place as you pull. That make sense?
Yes, I think I was actually asking for GAM 4, like when we had the two peaks in the 150 Kelvin, or the shoulder rather, like why is the shoulder on the right and not on the left? Should it not be symmetric about the rotation at about 0 degrees?
It's also because originally, if you look at, and it's not on the slide, but a free energy surface, sometimes for even at like 150 or 160 Kelvin, it's not even like in the simulation rotating, it just shows one. It will be between -60 and 0. So to get a full symmetrical 360 point of view, you have to combine different slides. So
Right.
sometimes there's just, with the lower temperatures, it's not moving, so there's not as much. It's, I guess, with movement, you get more data points elsewhere, and it looks a little more smoother and statistically accurate.
Thank you.
But I also think it's that, like, you have to really, this is where we have to go, is we have to really think about, like, what's the structure and what's the chemical environment. So as you rotate this one going from -180 to 180, maybe as you turn to the right, there's another close contact as you go right, so that it picks up, whereas the one on the left, maybe the close contact's on the left, right? So it really depends on the environment that terp-butyl group is in, and that's the point, right? Because if you go to the slide with the XRD comparison, like, you went kind of fast here, but this I think is really cool, where you took the occupancy from solving the X-ray data and getting, you know, electron density separations, and compared that to the free energy surfaces, and it lines up, right? And so I think that's what we're trying to do, is if you go back to the structure, like the Raman figure at the beginning, like the long range structure, if you look at how they overlap, this is a little bit different than what Dominic presented for the diterbutyl BT-BT system, where the long range packing was different as a function of polymorphic transition. Here, the long range packing is really similar. So the only thing that's changing really is, are the terp-butyl groups spinning or not? And that's enough to make the crystal crack, right? So trying to understand where that comes from is kind of the point. So I think if you can do that analysis for all the temperatures,
So more of the XRD comparison. Okay, I can do that this week.
because then that's the point. That's what we're trying to show. Like, why? Because then what we can do is we can dig into exactly what Simon's asking. Why is terp-butyl group 4 have 2 barriers, but terp-butyl group 2 has 1 barrier, and what is causing that? Is it because terp-butyl group 4 is slightly closer? Is it because there's correlated motion with another rotor? Like, I don't know the answer, but you have the data. It's just a matter now of kind of analyzing it.
Questions?
I mean, it looks like a very standard standard molecule, so I don't know why you shouldn't trust the standard force field. But did you recompute some parameters like for the dihedrals, or you just use the standard force field for your simulations?
This was the force field I used was actually from a postdoc of Giovanni Piccini's
Okay.
named Gentoo in Germany.
Okay.
But then that was for my original simulation at 350 Kelvin, and then last summer, once we looked like midsummer, we found out the phi and gamma, the two torpedoes were acting differently. We still use the same force field, but we had to recreate the unit cell positionings through high mole.
Thank you.
Of course.
Other questions?
Coffee break.
Yeah.